Hello everyone and welcome back to the class. In today's class, first of all, we will discuss about the properties of the conductor. So what is the properties of conductor everyone? Let's see it. Electric field lines originate and terminate perpendicularly at the surface of the conductor. Correct? So what is happening with the field lines everyone? It is terminating and generating perpendicular from the surface. And why it is happening everyone? Why it is perpendicular? Because when the field line is perpendicular to the surface, then charge present on the surface is in equilibrium condition. Because net force acting on that charge is what? It is a zero. Then only it can be in equilibrium condition, and we are assuming here all the charges in a equilibrium condition. So when it is equilibrium condition, then field should be perpendicular to the surface. This is the reason behind of this everyone. So what is happening? We have here uniform electric field. Intensity is E naught, and in this electric field we are putting one conductor. You can see it, we have one rectangle conductor we are putting inside this electric field. So what type of net electric field we will get? So when we are putting one conductor in the electric field, so first of all here redistribution of charge is happening. At this side we have negative charge everyone, and on this side we have positive charge. So one side we have negative and other side we have positive side. So here electric field lines are terminating everyone, you can see it at the negative side, and from the positive side field lines are generating. So at the one end it is terminating and at the other end it is generating. This thing is happening here. And what is the net electric field inside this conductor? It is zero everyone. Why it is zero? Because of that in the opposite direction we have electric field here. Correct? So in the opposite direction we have electric field E in, and outside electric field and inner electric field both are equal. So E naught equal to minus of E in. Why I am putting a negative sign? Because this electric field is present in opposite direction, that's why we are putting here negative sign. Alright, so E naught equal to minus E in everyone. So net electric field should be what? Inside this conductor it should be zero. Correct? So what is the net electric field inside this conductor? It is zero everyone. And it will happen with all the conductors. Now let's see one more example everyone. Now we are taking one spherical conductor and we are putting this spherical conductor in electric field everyone. So let's see what is the net electric field diagram when we will put this conductor in the uniform electric field. So let's see it everyone, what type of diagram we will get. So here we have negative charges. First of all, redistribution of charge is happening here. So one side we have negative and other side we have positive. And we are putting this spherical conductor in a uniform electric field. So at this side, field lines are terminating. Okay, so this type of field diagram we will get everyone. At one side it is terminating and the other side it is generating, and net electric field inside this conductor is what? It is zero again. So when we will put one spherical conductor in the electric field, so this type of net electric field diagram we will get, everyone. Note down. Let's see next topic, everyone. Force between positive negative point charge and the conductor. So here what is happening, we have one point charge, everyone, and we have one conductor, and this conductor is neutral, correct? Net charge on this conductor is 0. So what will happen when we will put one point charge and one neutral conductor, correct? So here we have a point charge, and on this point charge we have positive charge, and this conductor is neutral. But when we are putting this point charge near to this conductor, then here redistribution of charge will happen inside this conductor, everyone. So negative charge attracted by this point charge. So here accumulation of negative charge is happening. So on this side we have excess amount of electron, and this side we have deficiency of electron. That's why this part is positive, correct? We want to see it here. If we will put this point charge and this neutral conductor near to each other, then what will happen here? Attraction or repulsion. This thing we want to say it. They will attract or they will repel to each other. So if I will now break this conductor, or if I will divide this conductor in two parts with this imaginary line. So this is the center of charge of this side, and this is the center charge of this side, everyone. And this distance is how much? It is R1. And this distance is R2. Correct? So here between this left side part and this point charge, we have F1 force. And between this right side part and this point charge, we have repulsive force. So they are repelling to each other. According to Coulomb's law, we know one thing, everyone. Force is inversely proportional to the square of distance. Correct? So here we can see it, R1 is less as compared to R2. So if R2 is greater, so that definitely F2 should be less. Means F1 is greater as compared to F2. So if F1 is greater as compared to F2, so it should be attract, everyone. Net force is acting toward the point charge because F1 is greater. So between this both, what is happening? They are attracting to each other. So if we are putting one point charge and one neutral conductor near to each other, then they are attracting to each other, everyone. Here Coulomb's laws are not valid. Coulomb law is only valid for the point charge, correct? If I will apply here Coulomb's law, so formula is what? K Q1 Q2 by R square. Q2 should be 0 because it is neutral. So answer should be 0. But this formula is only valid for the point charge, not for the conductor, everyone. Now let's see its second case. Case number 2. This is case 1 and case 2. So what is the case 2, everyone? Now we have negative point charge and we have one conductor. So what will happen between these two? When we are putting one negative point charge and one conductor, then they will attract or they will repel. What will happen? Think it, everyone. So when we are putting nearer to each other, so what is happening here? Here again redistribution of charge is happening, correct? Inside this conductor we have negative as well as positive, both type of charge. So negative will repel to each other. So accumulation of electron is happening this side, and this side we have deficiency of electron. That's why it is positive. Now this is the imaginary line, everyone. It is dividing this conductor in two parts. This is the center of charge. So let's suppose this distance is R1 and this is R2. So here which one is greater? Definitely R2 is greater as compared to R1. So definitely if R2 is greater, then force should be less on that part. So F2 should be less as compared to F1. So here we have F1 force. They are attracting to each other, and between negative we have repulsion. And we know that F1 is greater than to F2. So net force is acting toward the negative charge, everyone. Correct? So net force is acting toward the negative charge, means here again attraction is happening. So if you will put one negative charge and one neutral conductor, so they will attract to each other. If you will put one positive charge and one neutral conductor, then again they are attracting to each other. So keep this thing in your mind, everyone. Note down. Let's see next topic, everyone. Relationship between charge density and radius of curvature of the conductor. So here we have relation, everyone, between the radius of curvature and the charge density. So we can see it here. If the radius of curvature is greater, then charge density will be less because we have inverse relation between this both. So keep this relation in your mind, everyone. It is important. And see what is the sense of this, everyone. Let's suppose here we have one conductor. All right. And on this conductor, we are giving some charge. So if I will put some charge on this conductor, so between these charges, some force will act and charge will distribute on this conductor uniformly. Because when we are talking about the sphere, then radius everywhere is same, curvature is same. That's why charge is distributing uniformly here. Correct? But always this thing will not happen. Always charge is not distributing uniformly. If I will take one square, everyone, now we have one cubical conductor and I am giving some charge, then what will happen? Then at the corner, charge density is greater. Why it is happening? Because radius of curvature at the corner is less and here charge density is very less. So here charge is distributing uniformly if we have one cubical conductor. And why it is happening? Because the radius of curvature at the corner we have less and at the flat surface radius of curvature is infinite. That's why charge density is very small at the flat surface. Correct? So always we will use this relation, everyone, when we want relation between the charge density and the radius of curvature. Now see this example also, everyone. Here what is happening? Here we have one isolated conductor, correct, in the heart shape. So if we will give some charge, then what will happen? Then if you will look this part, here the radius of curvature is less, everyone. But if you will look this, then it is the part of big circle. So let's suppose here center of this curve is line. So let's suppose this is R1 and this is R2. Correct? R1 and R2. So here R2, we can see it here, R2 is very large as compared to R1. So if radius of curvature is greater, then charge density is less, everyone. So let's suppose this is sigma 2 here and here charge density is sigma 1. Correct? So which one is greater? Sigma 1 is greater than to sigma 2. Why it is happening? Because radius of curvature at this place is less and here radius of curvature is large. That's why charge density is less. Alright, note down, everyone. Let's see next topic, everyone. Graph of electric potential due to hollow conducting, solid conducting and hollow non-conducting spherical bodies. So if you will see it, electric field versus distance graph for this all three cases, then it is same, everyone. This thing we knows. So let's suppose here we have one conductor and we know that if you will give some charge on the conductor, if it is hollow conducting, solid conducting and hollow non-conducting, so what will happen? Charge is only present on the surface in this all three cases. So charge is present on the surface only. That's why electric field is what inside the conductor is what is 0. Correct? So we know that inside the conductor electric field is 0. What about the potential? How the potential will vary? We know one relation, everyone, between the potential and the electric field, dV equal to EdR. This relation we know. Correct? We are looking for the change in potential. So electric field is 0 and integrate, everyone. E is 0 here, so we will put E equal to 0. So if we will do it integration of dV, then we will get del V. This is change in potential. and if you will do it integration of 0, then it is constant. Means if electric field is 0, electric field is not varying, then the potential is constant, everyone. If the electric field is 0, then change in potential is constant, everyone. This thing we are getting, means potential is not varying here, it is constant, everywhere it is same. Correct. So that's why when we are plotting potential versus distance graph, so from center to surface electric field is 0, that's why potential is constant, and outside what is happening, it is decreasing hyperbolically. Correct. So like if I will write potential at this P point due to this sphere, so what we will write, what it will be, everyone? Let's suppose the distance between center and P point is small r, and total charge present on this conductor is q. So potential at the P point can be written as k q by r. This is potential at the P point, kq by r. Correct. There is a potential. So here what is happening with the potential, everyone? It is decreasing hyperbolically. So inside the conductor potential is constant, and outside what is happening, it is decreasing hyperbolically. So this type of graph we are getting. Note down. Let's see next topic, everyone. Electric potential due to solid non-conducting sphere. So now we want electric potential inside solid non-conducting sphere. Correct. And here charge we are distributing uniformly on this solid non-conducting sphere. So the charge is present uniformly and it is everywhere. Correct. And let's suppose total charge is q, everyone. So we want electric potential. So let's suppose at this P point we want what is the potential, and this is the center of this solid non-conducting sphere, and this is O, everyone. At P point we want, and this point is present on the surface, and if the radius of this conductor, if the radius of this non-conductor is capital R, then potential on the surface can be written as kq by r, everyone. Correct. So on the surface potential can be written as kq by r, and we are assuming total charge is q, radius is r. So on the surface we know, so it is the kq by r, and at the P point we want, and let's suppose this P point is present at a small r distance from the O. Okay, so we want to determine at the P point, everyone. Now how we can find this thing? So what I will do it here, I will take one small strip in between this P and S. So I'm considering one small strip between this P and S point, everyone. And this strip I am taking at x distance from the center. So this strip is present at x distance from the center, and the thickness of this strip is dx. Correct? All right. So if I will write electric field at x distance from the center, so it is what this thing we knows already. Correct? What is the formula, everyone? It is rho x by 3 epsilon naught. This thing we knows. Inside the solid non-conducting sphere, electric field at r distance from the center can be written as what? Rho r by 3 epsilon naught. Here distance is x, so it is rho x by 3 epsilon naught. So electric field at x distance can be written as rho x by 3 epsilon naught. This thing we knows. If I will write this electric field in the form of charge, so it can be written as kq x by rq also. So if I will write in the form of charge density, so it is rho x by 3 epsilon naught, and if you will write in the form of charge, so it is kq x by rq. Correct. So this both things we knows, everyone. Now the next thing is what here? If I will write change in potential for this small thickness, so it can be written as dV equal to minus Ex dx. Here electric field is not constant. Correct. But for this small reason, this electric field can be considered constant, everyone. So for this small reason, we are considering electric field is constant and it is Ex. Ex value already we have. So dV can be written as minus Ex. And what is the value of Ex, everyone? It is KQX RQ dx. Correct? Now what we will do it? Now the next thing is we need to do it here integration, because we are looking at the P point. So we need to integrate here on both sides. We are integrating. And what should be limit of integration? So we are doing integration from P to S. So here Vp and this is Vs, everyone. This P point is present at R distance and this S point is present at capital R distance. So this is the limit of integration. Now the integration of dV is V. If I will put limit, upper limit minus lower limit, so it is Vs minus Vp equal to, now here we have KQ by RQ. This all things are constant, so put outside the integration. Then put this KQ by RQ outside the integration, everyone. Then inside the integration we have X dx. And limit of integration is small r to capital R. Alright. Now let's see next slide. Now the next thing is what? Do it here integration. Correct, at the P point we want. So let's see next step, Vs minus Vp minus KQ by RQ. Integration of X is what? It is X square by 2. And limit of integration is small r to capital R. Now Vs minus Vp equal to minus KQ by 2RQ. Put upper limit minus lower limit, R square minus small r square. This thing we will get. Okay. By looking at the P point, now simplify this. Simplify this bracket, everyone. So we have minus KQ R square divided by 2RQ. Minus minus is plus. So plus KQ R square by 2RQ. Correct? Now the next thing is what? Let's see it. Vs minus Vp, correct? So now the next thing is what? We are looking at the P point. So Vp equal to, we will get, put this Vp on this side and this term on this side, everyone. So Vp is becoming positive if it is going toward the right. So we have Vp equal to Vs plus KQ, and you can do it one more thing here. This and this is cancelling. So we have KQ by 2R only plus KQ R square by 2RQ. Now the next thing is what here? Multiply R square in the numerator and divide with R square. So if we will multiply and divide with R square, then next what we will get? And before multiplying, do it one thing, everyone. Put this Vs value, because Vs we know that potential on the surface formula is what? It is KQ by R, and this is KQ by 2R, correct? Plus KQ R square by 2RQ. Now do it one thing, add this both, then what we will get? Vp equal to 3 KQ by 2R plus KQ R square by 2RQ. Correct. Now do it one thing. If I will multiply with R square and divide with R square, then what we will get? So we have KQ R square by 2RQ, correct? And now what I will do it here, KQ by 2RQ, take common from both the term. So we have 3R square and sit here when it is going correct, VP equal to we are writing, so VS minus, this term is getting plus everyone, but this term will become negative when it is going toward the left. So here should be negative sign. So this is negative sign. Then finally we are getting KQ by 2RQ, 3R square minus R square. This is the final result, everyone. So this derivation is little bit lengthy, but this result is important for us. So at R distance, if we want a potential, so it is KQ by 2RQ, 3R square minus R square. And if you will look this formula, so this formula and this formula is same. Means our derivation is correct here. We got it same result, correct? KQ by 2RQ, 3R square minus R square. KQ by 2RQ, 3R square minus R square. Note down everyone. Then next we will discuss about the graph, potential versus distance graph, correct? Note down. So now we will discuss potential versus position graph. So already we have this result, everyone. Potential at R distance from the center can be written as KQ by 2RQ, 3R square minus R square. And this formula is only valid if the point is present inside the solid non-conductor. If the point is present outside the solid non-conductor, then this formula is not valid. So it is only valid for the internal point, correct? Alright, so here we want position versus potential versus position graph. This thing we want. So let's see how we will get this graph, everyone, how we can plot. So let's suppose this is solid non-conducting sphere and this is the center, correct? If I want potential at the center, so what we will get? So at center, small r equal to what? It is 0 because point is present on the center. That's why small r is 0 because small r is distance between the point and the center. So right now point is present on the center. That's why it is 0. Okay. So potential at the center can be written as V naught equal to KQ by 2RQ 3R square and small r is 0, everyone. So here we will get 3KQ R square by 2RQ. Now next thing is what? This and this is cancelling. Then what we have? V naught equal to 3KQ by 2R. So potential at the center, what we got it? Just 3 by 2 KQ by R. And on the surface already we know that. On the surface potential is KQ by R, correct? So if you will analyze this result, everyone, then you will get one thing. At the center we have greater potential as compared to surface, correct? So at the center we have greater potential, means if we are going from center to surface, then potential is decreasing here and it is decreasing parabolically from center to surface. So from center to surface we will get parabolic graph. So now let's see it, graph, everyone. So here we want potential versus position graph. Correct? So from center to surface, what is happening? Potentially decreasing parabolically. And from surface to infinite, what will happen? Potential will decrease hyperbolically. So now the graph will go like this, correct? So here potential is decreasing hyperbolically. Why? Because if point is present outside the solid non-conductor, then we will use this formula kq by small r, correct? And this r is distance between that point and the center. So here we are assuming all charges present on the center, correct? So this thing we are assuming when the point is present outside the solid non-conductor, or if suppose we have conductor also, then again this formula is valid. It is kq by r. So this type of graph we will get potential versus position graph. From center to surface, parabolically it is decreasing, then it is decreasing hyperbolically till infinite. Note down this graph, everyone. Let's see one question, everyone. On the basis of this concept, 27 drops of same size are charged at 220 volt each. They combine to form a bigger drop. Calculate the potential of the bigger drop. So here we want potential of the bigger drop, and the potential of the small drop is given. It is 220 volt, correct? So let's see how we can do this question, everyone. So what is happening here in this question? We have 27 small drops, correct? And we are combining this all 27 drops and we are making one big drop. Let's suppose radius of the big drop is capital R and the radius of the small drop is small r, correct? So radius of the bigger drop is capital R, radius of the small drop is small r. Okay, if I will write correct potential of the small drop, so it can be written as what? V equal to kq by r. I am assuming charge present on each drop is q, so it is kq by r, and it should be equal to 220 volt according to the question, correct? All right, and let's suppose this is equation number 1. Now the second relation we will get between the capital R and the small r if we will compare volume, correct? So volume of 27 drops and the volume of the big drops should be same because volume is conserved here. So what we can write here, volume of the small drop can be written as 4 by 3 pi r cube. And here we have 27 drops. So multiply with the 27. And the volume of the big drop is what? It is 4 by 3 pi r cube, correct? So volume of this 27 drops and the volume of the big drop should be same. Now simplify this and let's see what we will get. 4 by 3 pi get cancelled out. Here we have 27 r cube. If we will take cube on both sides, so we have here 3r equal to capital R. This is the relation, everyone. 3r equal to capital R. All right. Now we want potential of the big drop. So V dash can be written as, this is the potential of the big drop. So it is kq by capital R. Here q is what? It is the charge present on the big drop. I am assuming charge present on this all the small drop is q and charge is conserved, correct? So total charge on the big drop should be what? It is 27q because each drop has q charge, so it is 27q, correct? So V dash can be written as k, capital Q value is 27q divided by r, correct? This thing we are getting. Now put here capital R value also. So V dash equal to k 27q and the capital R is how much, everyone? It is 3r. This thing we are getting. Now simplify this. So we are getting 9k q by r. And what is the value of kq by r? It is 220 volt from the equation 1. So we are getting 9 into 220 volt. And if we will multiply this, then we will get 1980 volt. And this is the final answer, everyone. So the correct answer is option D, 1980 volt. So I hope this thing is clear, everyone, how we can do this question. Note down. Let's see next topic, everyone. Earthing of the conductor. So what will happen if I will connect one charge conductor with the earth? So what will happen? Let's see it. First of all, we will see it. What is the potential of the earth? So let's suppose the radius of the earth is RE. So the potential of the earth is what? It is KQ by RE. Let's suppose total charge present on the earth is Q. Correct? So potential on the earth's surface can be written as KQ by RE. We know that radius of the earth is how much? It is 64,000 kilometer. It is very large. So radius of the earth is very large. That's why potential is very small. Correct? So approximately potential of the earth is what? It is 0, everyone. Approx potential of the earth is what? It is the 0. Now we will see it. What will happen if I will connect one conductor with the earth, everyone? So let's suppose here we have one conductor and the charge present on this conductor is, let's suppose, Q dash, and we are connecting this conductor with the earth with the help of one wire. So if I will write potential of the conductor, so it is K Q by R, correct? And potential of the earth is approx 0. So we know that charge is always flowing from higher potential to lower potential. So what will happen when I will connect this conductor with the wire? Then charge is flowing from conductor to the earth, correct? And after some time, what will happen? The potential of the conductor and the potential of the earth is 0, everyone. So it is becoming equal, means it is approx 0. So if I will connect any charge conductor with the earth, then whole charge present on the conductor will move from that conductor to the earth, everyone. This thing will happen. And the potential of that conductor will become 0 after some time. So note down, everyone. Let's see next topic, everyone. Induction of charges. So here we have two concentric spheres, and at the center of the spheres plus Q charges present. We want what is the net charge on the inner and outer surface of this first and second sphere. This thing we want. So at the center plus Q charges present, and on the first sphere net charge is plus Q initially. So what is the net charge? This thing we want on the inner and outer surface. So let's see how we can do it. This question. So at the center plus Q charge is present, correct? So net charge on the center plus Q. So this plus Q charge attract minus Q charge. So on the inner surface, minus Q charge should be present. And we know that total charge is conserved also, correct? Total charge is conserved. So due to the induction on the inner surface, we have minus Q charge, and total charge present on the first sphere is what? It is plus Q. So if you want total charge plus Q, so on the outer surface, how much it should be? It should be plus 2Q, correct? Then only net charge is plus Q, because if I will add plus 2Q and minus Q, then what I will get? We will get plus Q, and the total charge present on the first sphere is what? It is the plus Q. Charge is conserved, everyone, that's why. Okay, net charge should be remain same. Now let's see its second sphere. So on the first sphere outer surface we have plus Q charge. So this plus Q charge attract minus 2Q charge. So on the inner surface we should have minus 2Q charge, correct? So on the inner surface we have minus 2Q charge, and the net charge on the second sphere should be what? It should be 0. The net charge on the second sphere should be what? It should be 0, because charge is not present on the second. So on the outer surface, how much it should be? It should be plus 2Q, because if I will add plus 2Q and minus 2Q, then again I will get the 0. So this is the distribution of the charges on inner and outer surfaces, correct? So here we are using induction of charges and we are using conservation of charges also. So if we will use this both rule, everyone, so we will get answer. Write down. Let's read one question, everyone, on the basis of this concept. Two concentric cells A and B have radii A and B as shown in the figure. The cell B is given a charge Q and the cell A is earthed. Find the charge appearing on the outer surface of the cell A. So here we want what is the charge present on the outer surface of A. This thing we want, correct? And on the B, how much charge we are giving? It is Q. So we don't know how much charge is present on the outer surface of the cell A, everyone. So I am assuming here it is Q dash, because we don't know, so we are assuming it is Q dash, and this Q dash value we want here. And on the B cell we are putting Q charge. So what is the potential on the surface of B cell, everyone? Think it should be what? Charge is Q. So can I write KQ by B? Correct? So KQ by B. This is the potential on the surface of the B cell. Now we want potential on the surface of A, everyone. So if I will write potential on the surface of A, then it is what? Due to this Q dash charge, the potential on the A can be written as K Q dash by A. And due to this B, the potential on the A can be written as what? It is K Q by B. Correct? This thing already we know that. If on the surface of the conductor, potential is, let's suppose V. Correct? Let's suppose we have one conductor, and on the conductor surface potential is V. Same amount of potential is present everywhere inside this conductor. Correct? This thing we knows. That's why on the surface we have KQ by B. So same potential is present on the surface of A also due to this B sphere, everyone, due to this B cell. Correct? Now see it here, we are doing here earthing also. Correct? So A is connected with the earth. So when I will connect this A conductor with the earth, everyone, so what will happen? The potential of A is becoming 0. So the potential of A is becoming 0. So now we have 0 equal to KQ dash by A plus KQ by B. And we are looking for what? We are looking for the Q dash. So here Q dash value is what? And KK is cancelling here. So finally we have minus Q by B into A. This thing we have. So minus Q by B into A. So the correct answer is option A, minus QA by B. This is the net charge on the A sphere or on the cell A. Alright, note down. Let's see next question. Determine the potential difference between the point N and M. So here we want potential difference between N and M point. So let's see how we can determine. So first of all, we will write potential at M point. So here we have two cells, cell number 1 and this is cell number 2. So M point is present on the surface of the cell 2. So Vm can be written as what, everyone? Potential at the M point. First of all, I am writing due to this minus 2q charge. So due to this minus 2q charge, potential at M can be written as what? K minus 2q by 2r. Then I will write potential due to this q charge at the M point. Correct? So it is plus kq by 2r. Correct? Now I will write potential due to this minus q charge at the M point. So it is plus k minus q by 2r. This thing we will get. Alright. Now let's see next thing, everyone. Potential at the N point. So due to this plus q charge, potential at N can be written as k q by r. Due to this minus q charge, potential at N point can be written as plus k minus q by r. And potential due to minus 2q charge at the end point is what? It is plus k minus 2q by 2r. Correct? This thing we will get. Now see it. Here we have k minus q by 2r and here we have kq by 2r. So this and this will get cancelled out. This is 2, this is 2, so this is and this is also cancelling. So here what we have? Finally we have minus kq by r. And let's see what is happening here. This is kq by r, this is minus kq by r, so it is cancelling. 2 is cancelling. So here again we have minus kq by r. So here we have minus kq by r, here also we have minus kq by r, correct? At both points we have same potential, that's why difference should be what? It should be 0, everyone. So finally we are getting here answer 0. So potential difference between AND and M point is how much? It is 0. Note down. Let's see next question. Two concentric cells A and B have radii A and B and charges QA and QB respectively. Find VA, VB and del V. So in the part A we want potential at surface A, potential at the surface B and the potential difference we want. And in the part B what we want? What will happen if A and B are connected by means of conducting wire? If I will connect A and B by conducting wire, then what will happen? This thing we want, everyone. So let's see how we can do this question. First of all, we will simplify part A. So first of all, I am calculating potential at the B, everyone. So let's suppose this is cell number 1 and this is cell number 2. So B point is present on the surface of second cell and charge present on the second cell is how much? It is QB, and on the first cell is QA. So what is the potential at the B, everyone? So VB can be written as K QB divided by B. This is potential due to this QB charge at the B. Now the potential at B due to this QA charge. So it is K QA divided by B. Right now this B point is present outside of this first cell, correct? So we are assuming here whole charge is present in the center and we are measuring distance from center to this B point. That's why we are writing here B. So when point is present outside the cell, then distance we will measure from the center. So keep this thing in your mind. So VB we got it. Now see it, what is the VA value? So what is the VA, everyone? So it is K QA divided by A. So potential on the surface of A is what? It is K QA by A. Alright. Plus next thing is what? Potential due to the second cell at the A point can be written as what? K QB by B. See, this A point is present inside the second cell, and due to this QB charge, potential on the B cell is what? It is K QB by B. So whatever potential is present on the surface, same potential is present inside the cell also. This thing we know. So that's why we are adding here K QB by B. Correct? This thing we are getting. Now the next thing is what we want here. VA we got it, VB we got it. Now we want del V. So we want del V value. So this is what, everyone, it is VA minus VB. So when we are subtracting this both, then we can see it here in the VB we have Q VB by B, and here also we have Q K QB by B. So this both terms are same here. That's why when we will subtract, then they will get cancelled out. So they are cancelling. Then remaining term we have K QA by A minus K QA by B. Now what we can do it? K QA we will take common and we have 1 by A minus 1 by B. Correct? This thing we have. So this is the potential difference between A and B. Correct? We got it, this thing. Now let's see B part, everyone. The B part, what is happening? What will happen if A and B are connected by means of conducting wire? So if I will connect A and B by the conductive wire, then what will happen? So think it, everyone. When I will connect A and B by the conducting wire, then the potential of A and B is becoming same. So it is becoming same, then the potential difference between A and B point is becoming 0 here. So del V is becoming 0. And what we have? We have del V equal to KQA 1 by A minus 1 by B. Correct? So if I will put del V equal to 0 in this equation, so what is the QA value? Think it, everyone. then QA is becoming 0 here. Means whole charge is moving from inner to outer cell. Correct? Whatever charge is present on the inner cell, that whole charge will move from inner to outer cell. This thing will happen if I will connect with the conducting wire. So I hope this thing is clear. Note down everyone.